In today's video, we're going to discuss how a directional coupler, or in this case a dual directional coupler, operates. These devices are kind of the heart of an SWR meter that is often used to measure how well matched an antenna is to a transmission line, or how well an antenna system is matched to the output impedance of a transmitter. So here's the schematic for the dual directional coupler that I built, or actually I built just a portion of this. And the hookup here would be, the output from the transmitter would hook into this connector here and go through the coupler and out to the antenna system, transmission line and antenna system. And then through a little bit of kind of algebraic magic, if you will, with these two coupling transformers, we couple some energy onto a second line here, and we're able to essentially measure a signal that is proportional to the forward power being delivered from the transmitter to the load, and measure a signal that's proportional to the reflected power coming from the load back towards the transmitter. So we'll discuss how each of those voltages are formed and how this works. There are many different types and designs for directional couplers, or in this case a dual directional coupler. The design shown here is very commonly used by amateur radio operators, since it's very easy to build. It's got 50 ohm impedances on all ports, and actually you can change that by changing the impedance here, make this operate, say, for a different line impedance. And it's got pretty darn good directivity for something that is homebrew. For a good definition on things like directivity, you may want to take a look at another video I did that talks about just the basics of directional couplers and how you use them. This video is going to talk more about how this thing actually operates. Now, when used in an SWR meter application, what we're going to typically do is take the voltage at this node, which is proportional to the forward power, and do a little bit of an amplitude detection on that to essentially give me a DC value that I can use to drive a meter to measure forward power. And similarly, we'll detect the power for the reverse direction and detect that as well. And then by looking at the ratio between these two, we can compute or calculate or graphically show on a meter what the voltage standing wave ratio, or VSWR, is on that line. But for this video, I really just want to focus on how the directional coupler itself works, okay, because the rest of this is actually pretty simple. Now, one thing you might notice about the schematic, if you look at it carefully, it's symmetric, kind of top to bottom here. So the main line going through is essentially a single turn through the transformer on both sides, and then we've got essentially the multi-turn secondary of the transformer, if you will, going up to the other line. So we can see if we literally turn this circuit over, it's basically the same circuit. We can swap things around and it's the same thing. So it's really kind of a very simple symmetric circuit to build. And it also makes it a little bit easier to break down what's going on in this circuit to understand how it operates. So let's go take a look at that. Now we can see the symmetry in the design just by the way that I put this thing together. Both sides of this are kind of almost mirror images of each other. So you really could kind of arbitrarily pick which side is going to be our RF path and which side is going to be the path that we use to detect the forward and reverse power. Now, one thing you may note in looking at my construction here, this directional coupler that I built does not include these 50 ohm resistors and does not include the amplitude or diode detectors on either side. The reason is that in order to kind of show and demonstrate how this circuit operates, I decided rather than solder in the 50 ohm resistors here, I'm going to simply connect up coaxial leads at these points and then terminate those in the scope using the 50 ohm terminations in the scope. And that will allow me to take advantage of the symmetry of the circuit to turn it around to kind of take a look at essentially how each half of this circuit works and how those two things combined together conspire to give us our forward and reverse voltages. So let's go take a look at how this thing works. Now, the math behind how the directional coupler works might look a little intimidating, but it really is pretty simple. And of course I'm going to make these notes available through a PDF file that you can download from a link shown below in the video notes. So let's quick define a couple of kind of definitions here. So let's say our RF signal path is going to be from this direction, from say the transmitter connected at RF in, going out to a load connecting at RF out, an antenna or something like that. So for the signal being delivered in the forward direction, or the forward power, is going to have essentially a voltage and a current. That voltage and current relationship is essentially going to be equal to the line impedance. So we can say that the forward current is equal to the forward applied voltage divided by the line impedance. Similarly, if we've got some signal being reflected back from a load, okay, the voltage and current relationship of that is also going to follow that same line impedance relationship. However, we use a negative sign here because the current from the reflected from the load is actually going in the opposite direction from the current that's flowing towards the load. Now, of course, by superposition, these things will all add up. So the voltage on the line at any point in time is going to essentially be equal to the sum of the forward voltage plus the reverse voltage at that location on the line. Similarly, the currents will also add. Okay, we're essentially the forward current and the reverse currents add up. Now, of course, the reverse current has a negative sign, so it's like adding a negative, which is the same thing as doing a subtraction. Now, if we substitute the formulas for IF and IR here, we wind up with this equation that says that the line current, okay, is equal to the forward voltage minus the reverse voltage at that location on the line divided by the line impedance. And we can see from the construction of my dual directional coupler here that it basically almost physically matches the drawing that we've got up top here. I've got a transmission line coming through here, and that's going from this connector to that connector here, going through the transformer. The secondary of the transformer is coupling down across onto this second line, which is connected to these two ports. Same thing in the other way. We've got this transformer here that's got a single turn with this line down here, and then our multi-turn secondary kind of going up to the line on the other side, just going through this plane. Using a copper plane here to avoid capacitive coupling across the two halves here. And you'll notice, if you look carefully, that the coaxial line that I've got going in here, I've only got the ground connected at one side. Because the idea is that this doesn't really need to be an extension of the transmission line. I just want to ensure that I minimize the capacitive coupling from that line to the windings on the secondary. So by connecting only one side of the shielded coaxial cable here, what we're doing is essentially creating a Faraday shield to minimize the capacitive coupling from the line to the secondary. Now, the last thing that you may notice if we look at this is, again, these 50 ohm resistors are not included in the construction here, at least at the moment, because I'm going to basically terminate those lines using the 50 ohm terminations in the scope when we go to make our measurements. Now, the key to understanding how this directional coupler works is to recognize that we're actually sensing both the line voltage and the line current. Now let's take a look at how that happens. The line current is sensed here, the line voltage is sensed here. So let's take a look at each of those separately. So let's just consider this transformer here first, and that's sensing the line current. Any current that's flowing through here is going to be, kind of induce a current in the secondary of this transformer that is n times less than the line current, and that n is the turns ratio between the primary and secondary. So we'll have a small sample of this current flowing down here. Now, as that current enters into this node here, it splits between the 50 ohm load on this side and the 50 ohm load on that side. So it essentially sees, say a 25 ohm load. So the voltage that's generated both here and here are going to be the same, essentially in phase, okay? And it's very easy to determine what that is. All right, so let's call that, at least the voltages generated by the current sense, let's call them V forward prime or V ref prime. And of course they're equal to, this line current divided by N multiplied by the line impedance divided by 2, because I've got 2 of those and the current is splitting. So if we substitute the line, the formula up here for the line current down here and multiply this out, we can say that V forward prime and V ref prime is simply equal to the forward voltage minus the reverse voltage divided by 2N. So let's just keep that in mind. So let's go take a look at that on the scope. What I'm going to do is disconnect the other transformer that's here and only have this one in. So we'll put a voltage, through the line on this side, and then measure what's going on these two ports. Okay, so we've got this hooked up to the scope. I've got a 14.2 megahertz RF signal, 20 meter signal coming into the RF input. The output is going to the scope, being terminated in 50 ohms at the scope. And I've got these two ports connected to channel 3 and channel 4 of the scope using the 50 ohm terminations in the scope. So let's turn the signal generator on here. And channel 2 here is the signal that's coming through the line and coming out of the output here. So that's going to channel 2. Channel 3 and 4, okay, are looking at these two nodes here and here. And that's actually the two channels here. Now it looks like I've just got one, but if you can see, these two signals are in phase. So they're essentially giving me a signal that is proportional to the forward current in this line. So the forward current gives me a signal at the forward and reflected ports that are in phase with the current in that line. Now of course that's only half the story, because we're only using one of those transformers. The other one I've got disconnected. So let's take a look at the other half, and let's not consider this half here for the moment and just consider what's going on with this half. So I've got that down here. Now this half actually senses the line voltage, okay? Because the voltage that's appearing here is appearing across this multi-turn side of the transformer. So that looks like a relatively high impedance. This is just going to basically sense that voltage and impress essentially a voltage at the secondary, essentially across, from one side to the other, that is proportional to the voltage that appears at the line. And I kind of did this with my fingers kind of intentionally, because if we look at the way the load is connected, I've got a 50 ohm load to ground here, a 50 ohm load to ground here. The voltage is impressed across the secondary, from one end to the other. So what we're going to see is essentially this signal flip back and forth, or essentially seesaw around ground. Okay? So one side goes up, the other side goes down, and vice versa. And that voltage that appears on one side or the other of the seesaw is again proportional to the line voltage. Okay, if the line voltage is the forward plus the reverse line voltages, the voltage appearing across here from one side of the transformer to the other is going to be that voltage divided by N, where again N is the turns ratio of that transformer. Now of course, since half that voltage is going above ground and half is going below, we get another factor of 2 in here. So let's say V voltage, or we'll call that V forward voltage double prime, because it's the kind of the other side here, is 1/2 of that voltage, and then the V ref double prime is negative 1/2 of that same quantity. Okay, again, because these things are symmetrically bouncing around ground, because ground is connected here and here. So if we simplify that, we basically say that the V forward double prime and V reflected double prime are equal to these two quantities. Basically the same thing, but with a negative sign. So let's go hook that up and see what that looks like on the scope. Now of course the beauty of the symmetry of the circuit, as I mentioned earlier, makes it real easy to go from this configuration that we just tested to this configuration. All I need to do is flip this thing over. So that's what we've got now. I've got my RF signal coming through here. Okay, where the disconnect here is basically taking that transformer out of the picture, so all we're left with is this transformer down here. And now we're looking at V forward and V reflected on channel 3 and channel 4 down here. And now here we can see that we're sensing the voltage here, and the voltage that appears at the V forward and reflected ports are opposite phase from each other. Okay, remember in this case those two signals were in phase. In this case they're 180 degrees out of phase, and we can see that happening right here. So and this is really the key to see what's going on. By sensing the current and the voltage in this way, and by essentially having these two signals appear in phase, these two appear out of phase, by having everything matched in terms of this transformer matching that transformer in terms of turns ratio, having these load impedances match, we can basically make the math do some magic for us. So here's the magic. Remember, we're just applying superposition here. We defined essentially what was going on, at the contribution of the voltages at the forward and reflected nodes here from this path and from this path. So we can simply add those up. So we can say the total forward voltage appearing here is equal to this guy plus this guy. So if we add those two things up, we basically say that that forward voltage is essentially equal to the forward line, or the forward line voltage divided by the turns ratio. Similarly, if we take the voltage at the reflected node, we can add up those two voltages, this one and this one. So if we add those up here, what we wind up with is saying that the voltage at the reflected port is equal to only the reflected voltage divided by N. Now, of course, there's a negative sign here, but you have to remember that these two things are going to essentially flip back and forth. And when we go through the detectors for measuring the the power with, say, with an SWR meter, we're only going to detect the positive half. So the real key to this is that what we've done now is created voltages at these forward and reflected ports that are proportional only to the forward voltage and the reverse voltage. So let's go prove that to ourselves, and we'll basically reconnect both transformers and take a look at what's going on at the forward and reflected ports when we do things with the output impedance to mismatch the load. Well, we've reconnected both transformers here, and the directional coupler is working properly. I've got an RF signal being delivered in from the signal generator, going through essentially the top of the directional coupler here, coming out here and being properly terminated at the scope input here on channel 2, and that's that signal. Now, of course, remember, we're measuring or sensing both line current and line voltage, and the resulting voltages we get at these ports is essentially proportional to the forward delivered power to the load and the power that's reflected from the load. Okay, we're going to measure that as voltages at this end here. Now, if we look at these two ports, these are connected to channel 3 and 4 on the scope, and what I can see is one of these is flatlined, and that's actually the V reflected. That's indicating that I've got no reflected power coming back from the load because I've got a perfect termination of 50 ohms. And then channel 4 is connected to V forward, so showing me the forward power that's going towards the load. Now, of course, if we misterminate this line, disturb the impedance match, for example, if I change the termination impedance on channel 2 from 50 ohms to, say, 1 megohm, that's going to create an impedance mismatch, and therefore we're going to reflect energy, nearly all of the voltage, back from this port and back through the other direction. So let's turn on channel 2 and change its termination from 50 ohms to 1 meg, and watch what happens. Okay, the voltage, that's appearing at this node actually doubles, right, because we're not loading it with 50 ohms anymore, so we don't get that 50 ohm voltage divider from the source impedance. That voltage doubled, but also look what happened here. Now my reflected voltage to channel 3 trace, the purple trace here, is now basically equal in amplitude to the forward power. Now notice that the forward voltage didn't change. If I change that termination back and forth, you'll notice that the channel 4 voltage waveform here is not changing, because we're still essentially delivering the same amount of voltage from the signal source in the direction towards the load. But what's the difference is that as I change the load impedance, I'm either absorbing all of that energy at the load or I'm reflecting it back towards the source. So we can see we're actually really just measuring the forward and reverse voltages here. Now let's look at the other extreme case. Let's actually just short out the load. Okay, so we've got our signal coming in here. I'm just going to short it to ground with the screwdriver, and we can see what happens is that the voltage on the line goes to 0. Okay, that's channel 2, because we've essentially just shorted it out. It's like we've got no voltage there anymore. And you'll also notice again that the green trace, channel 4, which is the forward voltage, is still remaining the same, but now the reverse voltage is equaling in amplitude and actually equaling in phase in this case. Okay, so tough to get a perfect short here with the screwdriver. There we go, that's pretty close. So we can again see that in these two extremes, going to a very high impedance or a very low impedance, the forward port is always still showing me the delivered power in the forward direction, and then the reverse power is showing me, or the reverse port is showing me the amount of energy being reflected back from the load. All right, one final example here. Again, I'm back to that perfect termination situation here, except I installed a T in the connection here. So right now at the other end of this T open, we're essentially seeing still that perfect 50 ohm termination at channel 2. If I take a 50 ohm terminator and stick it on the other node here, now I can actually see I do have some reflected power. It's not at the full amplitude of the forward power, and again, our resulting line voltage has changed a little bit. But even with that, again, the forward power as being shown by the V forward port is still staying the same. So, and this is the basic principle behind an SWR meter, is we're essentially measuring the ratio between these two voltages, and then from there the scale is basically printed to read out in SWR. And so I hope you learned a little something about how a dual directional coupler works that is typically found in an SWR meter, and actually how fairly simple it is to actually build one of these, and essentially what the operating principle is, and how we can essentially extract essentially a signal proportional to the forward power and a signal proportional to the reverse power in order to measure SWR. Again, this design that I've got shown here has been published many times. You'll find it in many of the various years of the ARRL Handbook, and that's basically the design that I have here, so you can look up the details there, and lots of places to find it online as well. Anyway, thanks again for watching. Again, I hope you got something out of this. If you like what you see, please subscribe if you haven't done so already, and comments and questions are always welcome. Thanks again for watching.